Hello again, and welcome to the third lesson on multithreading in C++. In this lesson, we'll provide a quick overview of the multiprocessing mechanism, which will help us understand how the multithreading mechanism works in later videos. We mentioned in the previous lesson that a process is any running instance of a software on your computer. We also described that multiprocessing is the system's ability to run multiple processes concurrently or simultaneously. So how does the multiprocessing mechanism work? To explain this, I'm going to use three software: Apple Music, Safari browser, and Microsoft Word software. From each software, I'm going to call one process: an Apple Music process, one Safari browser process, and one Microsoft Word process. Also, I'm going to use a CPU like the one I used in the previous tutorial. As you can see, this CPU has three physical cores. The top core uses hyperthreading, so it has two threads. The other two cores are single physical cores, each with one thread. This means that the total number of threads in this CPU is 4. When you switch on your computer, a software component called the scheduler is immediately activated and assigns each CPU thread an ID, such as 0, 1, 2, and 3. Also, the scheduler decides the CPU thread where each process will be processed. In our example, the scheduler has decided that Microsoft Word will be processed in the CPU thread 0, the Safari browser will be processed in thread 1, and Apple Music will be processed in thread 2. In addition, the scheduler also assigns each process a unique ID called the process thread ID. Important to note that once the CPU thread ID and the process thread ID are assigned to a process, they stay constant throughout the process lifetime. Now, to run each process, the scheduler divides each process into chunks of bytecodes that vary in length. Each chunk is expected to be processed at a defined time under demanding timelines calculated in nanoseconds. Moving on, the scheduler has decided that a chunk of bytecode from Microsoft Word will be processed at time t0, and a chunk of bytecode from the Safari browser will be processed at time t1, and a chunk of bytecode from Apple Music will be processed at time t2. This pattern continues at times t3, t4, t5, and so on. The decision on the order in which bytecode is processed is based on priority. Notice how the chunks of bytecodes are now organized and waiting to be executed at a defined time. The method of organizing executable bytecodes under demanding timelines is called indexing. Now, to send these bytecodes to the CPU, the operating system uses another software component called the dispatcher. The dispatcher takes each chunk of data and sends it to the CPU at the correct time for processing. Note that the dispatcher is highly synchronized with the scheduler to ensure a smooth experience on your computer inputs and outputs, and their job carries on as long as there are processes running in the memory. To ensure that the concept of indexing is understood, I organized the information provided by the scheduler in this table. From the table, at time 0, the dispatcher sends to the CPU a chunk of bytecode from Microsoft Word along with the process thread ID, CPU thread ID, and the processing time. At time t1, the dispatcher sends to the CPU a chunk of bytecode from the Safari browser along with the process thread ID, the CPU thread ID, and the processing time. Note that T1 is equal to T0 plus the processing time IT0. Once T1 is processed at time T2, the dispatcher sends a chunk of bytecode from Apple Music along with the process ID, CPU thread ID, and the processing time. The same action happens at times T3, T4, and so on. As a software engineer, unless you are designing an operating system, you don't need to be involved in any of this information. However, you may often need to know the process thread ID. In fact, this is the only information that will be provided to you as a software engineer. The process thread ID is also called the root thread ID by the operating system. However, in software engineering, we call it the parent thread ID. You'll learn why we call it the parent thread ID later when we talk about multithreading, but from now on, I will always be calling it this way. In C++, you can get the root thread ID using this code, or this more practical code. You're welcome to test these two samples, but you don't need to worry too much, as you will learn a lot more about it when we start coding. Here is a summary of what you've learned in this lesson. Please note that multiprocessing is a complex subject, so I hope I managed to make it as simple as possible for you to understand. Thank you for watching, and I look forward to seeing you in the next lesson.